Okay, we're going to talk about reversible reactions and equilibrium. This is another very important topic. Back in the early 1900s, chemists found a way to take ammonia and nitrogen and hydrogen and form it, making ammonia from nitrogen, hydrogen. Sorry, I was saying that incorrectly. So this was huge for agriculture. They were able to make fertilizer through the Haber process, and so they were able to kind of tinker with the chemistry and figure out how to make this. It was very important and very important for chemistry and very important for ag. So how do the amounts of reactants and products change in something that's in equilibrium? So some reactions can go forwards and backwards, and we'll see that when we get to acids and bases. So at chemical equilibrium, no net change occurs in the amounts of anything in the system, but actually molecules are forming and molecules are breaking apart. It's just that the amounts you have of everything remains the same, even though individual molecules are changing. So it's just like when you go to the shopping mall, there's going to be some people going up the escalator and some coming down. In a chemical reaction, you have some reactants going that way and some products going back to where they started, going around and around and around. That's equilibrium. A reversible reaction is one in which the conversion of reactants to products and the conversion of products to reactants happens at the same time. It's just like this escalator. Yeah, some people go that way, some people go that way, and the rate of the number of shoppers going up compared to the number of coming down, that rate of people going up, people going down, is constant. So let's look at one. We have SO2 and O2 together. They react to make SO3. We're not at equilibrium yet. And so this happens first. Let me go backwards. We've got this in a container. Some of it reacts to make SO3. So you have SO3. And then some of these guys decide to break down and go back that direction. And when the rates are, all these things are happening, then we're at equilibrium. When this double arrow is happening, when you have that going this and this forming into that, and when these guys are breaking apart and forming those two, then you're at equilibrium. So you have to start off at the beginning, go to products, and then products have to start reversing to reactants, and so you're going back and forth, and all three of the molecules are present all the time. So you have SO2, O2, and SO3 at all the time, around all the time, at equilibrium. The rates of the forward and reverse reactions are equal, so how many moles are changing per time is going to be equal for both sides, both directions. And the relative concentrations of the reactant and products are called the equilibrium position of the reaction. So the rates are equal, but not necessarily the concentrations of those things. So you'll see graphs like this a lot where you're starting off with the beginning concentrations of things, 0 for the SO3. This is what I showed you at the beginning. I had some O2 and I had some SO2. They're starting to react and they're starting to form SO3. So you'll see graphs like this. So I hope you can understand this. What 3 things can you do to change a chemical equilibrium? So this is called Le Chatelier's principle, and I definitely have questions like this on the quizzes and tests for this section. So Le Chatelier says that after we get equilibrium, the system wants to stay that way, and the system will change to go back to the way it started when it was in equilibrium. So we can change the equilibrium. We can stress the equilibrium by changing how much we have of reactants or products. We can change temperature, and we can change the pressure. All those things we can stress the system, and the system will try to go back to the way it was before you added the stress. So Le Chatelier came up with this. It says if a stress is applied to a system, when a system is in equilibrium, the system changes in a way to relieve the stress and try to get back to where it was before. So you have an equilibrium in your blood of CO2 and carbonic acid, and this system tries to keep your pH of your blood in the right level. So it's very important. We're trying to always keep the right pH level in our blood. It's very important for all of our systems. Temperature, so concentration can really affect, we can stress the system by changing a concentration. We can stress the system by changing a temperature. So this is showing you that this is equilibrium, and when it's warmer, it goes more towards this color because it has more of the dark nitrogen dioxide. And when you cool it, it goes over here, and then it has more dinitrogen tetroxide. So we can stress the system with temperature. We can stress the system with pressure. Pressure is going to affect any gases that are in your system. So we can change the pressure, and it's going to affect what, if you're going to go towards the reactant side or the product side. Okay. So let's look at, this is like a typical problem I would give you for Le Chatelier. So it's saying that you need heat on the side to react with, you're going to have heat on this side. It's endothermic reaction, and you're going to have one compound, this compound on the left. And when these react together, you're going to form these two products on the right. They're all gases, so pressure is going to affect the system. So if I add Cl2, I'm going to add more Cl2, and the system's not going to feel like it did when it started. So it's going to try to get rid of some of that excess Cl2. So it's going to want to make the reaction go that direction. Okay? So that's what would happen if you add Cl2. If you increase pressure, this is a harder one. You have 1 of gas, and you have 2 moles of gas on this side. So if I increase the pressure, this is going to try to get back to the pressure it felt before, so left direction, to get rid of some of these gas particles, so you'll have lower again. So that's kind of a harder one. You need to think about that one. If I get rid of heat, the reaction is going to want to go to the left to make more heat to be in balance the way it was when it started. If I remove some of this, the system's not going to be happy because it used to have this in there, so it's going to go this direction and make more of this PCl3 to feel like it was at the beginning. So those are questions you would see on a quiz or a test. Very important, so make sure you're understanding that and read through the book about this part. So here's the answers for that. So pause that, look through that. I explain them, but make sure you read through these. This will help you a lot. Here's another question you could try on your own. So we're going to be able to figure out a math equilibrium constant called KEQ. K is always in chemistry is a constant. So we're going to look at how to figure out the math of this. So KEQ is a ratio of products over reactants, and these brackets mean molarity. So we're going to use these letters are your products, these letters are our reactants, and these things are exponents, and these have to do with the balanced equation. These are the numbers, the coefficients in front. They go here as exponents in this KEQ. So if you have a KEQ bigger than 1, that means you have more products than reactants. If you have KEQ less than 1, you have more reactants than products. So let's see if we can figure out how to do this. So we have a liter of a gas mixture at 10 degrees. It has that many moles of that guy and that many moles of that guy. Luckily, they gave us as a liter, so that tells us the molarity. That many moles in 1 liter, that many moles in that liter. So we can use that information. This is balanced, so we have 2 N's, 4 O's, 2 times 2 is 4 O's. So it's all set up, ready to go. We need to balance this before we start, and we're good. Now we need to figure out the KEQ. So we're going to use the numbers they gave us. that many moles per liter, that many moles per liter, and we want to find KEQ. So it's set up like that, products with their exponents over reactants with their exponents in molarity. It has to be molarities brackets. So we have, if you go back to the balanced equation, 2 NO2s, 1 of these guys. So 2 of those, 1 of those. So I have to square this number here. So try that in your calculator. Make sure you can get this. Excuse me. And let's look at sig figs 2, 2. So 2. And there's no units for this. So don't worry about the units so much on this. Generally, we just write A, because they get like really weird. So here's one for you to try. And here's another KEQ we can try. This has 1 mole in 1 liter and 1.56 moles of this guy in 1 liter. So they gave us, we can figure out molarity real easy. This is going to be 1 molar and this is going to be 1.56 molar. 1, 1, and 2 is the balanced equation. And so we have 1, 1, and that is the product. If we, oh, sorry. So I almost got tricked because I didn't read this carefully. 1 mole and 1 mole of hydrogen, iodine, 1 and 1, beginning. This is initial conditions. And so if I have 1 here, 1 here, I have to make sure I'm thinking about what's happening in equilibrium. So they're saying what through, let's look at what happens in equilibrium. I applied to this guy, but it's a 2-to-1 ratio. So I should have that amount for this one and this one when we're at equilibrium. So let's go through that carefully. So initially I had these molarities, but at equilibrium I have this as my product. So let's figure out how much I have of everything before I start working on this problem. So I had 1 mole of each of these guys initially, but when we're at equilibrium, we have 0.78 used up to make that 1.56 of the product. So this is a little more complicated. So we have this. So we're going to use that information as our equilibrium concentrations for our reactants. And then they told us how much we have of this at equilibrium. They didn't tell us how much we had of this at equilibrium, so we had to figure that out ourselves. So this is kind of a trick. Take this one slowly and carefully. And then you're going to do the math on that. And there's no units for that. So try this in the calculator, make sure you're good on that. And then you'll get a K of 50. So try that one yourself. This one's a little bit trickier because you have to remember that you have to figure out equilibrium concentrations. Here's one to try for you. And let's try a quiz. In a reaction to equilibrium, reactants and products are, so they're forming at equal rates. Remember, the rates are the same, but not the concentrations. So we're talking about pressure here. So this has 2 moles here, 3 moles on this side. So if I increase pressure, which way does that reaction want to go? And we should have a double arrow here. Sorry, that's misleading, but this is an equilibrium right here. So we would want to go this direction because this side we have 3 moles and this side we have 2. So if we increase pressure and we go that direction, it will reduce the pressure. It would not affect equilibrium. So volume only. Here we have a KEQ of 1. So how are we going to figure out concentrations of everything? So try that one. And you should get that these are equivalent because anything over itself is going to be 1. All right, so I hope you enjoyed that. That's important about Le Chatelier, so make sure you understand that. I'll talk to you soon. Bye-bye.